Hello, this is Math 2231 coming to you from the College of DuPage during the summer of 2020, and our discussion topic is epsilons, deltas, and such. Let's take another look at the informal definition of our limit. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is L. And we write it this way. The limit as x tends to c of f of x equals L. At first glance, this seems fairly technical, but even so it is informal and imprecise because exact meanings have not been given to the phrases f of x becomes arbitrarily close to L and x approaches c. So what we're going to talk about today is the epsilon delta definition that is used in mathematics. It is tradecraft for professional mathematicians. So in this figure over here, we let epsilon, the lowercase Greek letter epsilon, looks like an E, represent a small positive number. And so we're at L, we go up to L plus epsilon and down to L minus epsilon. And so if I wanted to describe that interval using absolute values, I would say the absolute value of f of x, which is this graph right here, is minus L is less than epsilon. That means f of x is within epsilon of L. Similarly, the phrase x approaches c means that there exists a positive number delta. The delta number is down here. Delta looks like a D, such that x either lies to the left of c or to the right of c, but both of these facts can be expressed by this inequality. 0 is less than the absolute value of x minus c less than delta. Now the first part of this inequality, 0 is less than x minus c, means that the distance between x and c is more than 0. X is not equal to c. The second piece, this piece, says that x is within delta units of c on either side. This is delta and this is delta. So the definition then we have is let f of x be a function defined on an open interval containing c, except possibly at c. We don't care what happens at c. And let L be a real number. If we say the limit as x tends to c of f of x equals L, that means that for each epsilon greater than 0, there exists a delta greater than 0, such that if 0 less than absolute value of x minus c less than delta, then the absolute value of f of x minus L is less than epsilon. That is the epsilon delta definition. So here's a problem. What we're supposed to do is, given that the limit as x tends to 3 of 2x minus 5 is equal to 1, and of course it is, you just plug it in, put 3 in there, and you say you get 1. But what we want to do is find delta such that the difference between f of x and L is less than 0.1 whenever we are within delta of 3. If you look at the picture, what we say is, oh, so we were y equal 1 is what our limit value is. This is the graph of f of x, and so we go up from 1 plus epsilon and 1 minus epsilon that we have in this problem, and we go over and we drop the perpendiculars to find out what are these function values, and we find that they're x equal this number or x equal this number around 3. And the difference, if you go this way or you go this way, is always 0.005. Now you can also notice that if I take the absolute value of 2x minus 5 minus 1, that's really equal to 2x minus 6 in absolute value. And I can factor a 2 out of each one of those and pull it out, so I have this. Now if I look at this, I say, oh, if I want to make this thing less than 0.01, it's sufficient for me to make this thing less than half of that, because when I multiply by 2, then it'll be less than that. So that works. So the delta that we find is, just like in the figure, it is 0.005. So you see, given epsilon, we found delta. Given epsilon, we found what delta had to be. Here is another example. It says use the epsilon delta definition of a limit to prove that this is true, that the limit as x tends to 2 of 3x minus 2 is equal to 4. Now we know that is true because if we take 2 and just plug it in, we get 6 minus 2 is 4, and so we knew that. They really didn't have to tell us that. But now we have to, for any epsilon. Now we're not taking a specific number, it's just epsilon, the variable. So we have to find delta in terms of epsilon. So we must show for any epsilon greater than 0 that we can find a delta such that the absolute value of this is f of x minus L is less than epsilon whenever this is true. Now, because your choice of delta depends on epsilon, you need to establish a connection between the absolute values of this and this. But look what happens when I do the arithmetic again. I have f of x minus L is equal to this, but I can factor a 3 out of there. And so you see, if I take, for any epsilon greater than 0, I can take delta equal epsilon over 3. This works because if this is less than epsilon over 3, then f of x minus L is less than epsilon. Here's the kind of problem I could ask you on a test, and this is very close to the kind of problem I'd ask. I will not ask you exactly this function, but I'm giving you an epsilon. So the question is, here's a graph, and you want to find delta such that if x is within delta of 1, then f of x is within this epsilon value of 1. So you see at the top I'm getting 1.1, at the bottom I'm getting 0.9. So here's how you go about it. You need to find a delta such that when 0 is less than the absolute value of x minus 1 less than delta implies that the absolute value of f of x minus 1, and I can calculate what that is because I know what f of x is. I get this is less than 0.1. So we start working with this. Now what does it mean for the absolute value to be less than this number? Well, it certainly means that this number is caught between negative 0.1 and positive 0.1. And if I add 1 everywhere, I will get that 1 over x in the middle is between this number and this number. Now I can turn all these things upside down because I really want to know about x minus 1. So if I turn them upside down, the inequalities change. So x is bigger than 10 over 9 and less than 10 over 9. And now I subtract 1, and I find that x minus 1 has to be between 1/9 and 1 over 11. So we have to take the smaller of the two because both must work. So we take delta equal 1 over 11. Then whenever this is true, this will be true. And you work your way all the way back up the identity, and you will see that this is true. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless.